Hello and welcome. In this video, we're going to take a look at the sort of standard maximization problem that occurs in linear programming. A very nice type of problem that also allows us to use a very straightforward algorithm to be able to solve. It's called the simplex method. It's an algorithm because as long as you follow the rules and procedures of the simplex method, you should arrive at the optimal solution, assuming that one can be found, assuming there is a feasible solution. And it's a little bit tedious to do by hand. We're going to have to do quite a few row operations on some tableaus, but doing it at least will kind of enlighten you as to how this method works and how you see just like a computer can do this so quickly. So let's take a look and see what a standard maximization problem looks like for linear programming. There's a few different criteria that we have involved. The first criteria might be a bit obvious. We have to have a linear objective function that is to be maximized. That's why we're looking at a standard maximization problem. The second criteria is that all of the variables in the problem are non-negative. Last but not least, also just as important, all of the constraints must be in the form of linear expressions of the variables that are less than or equal to a constant. So I've got an example here. Profit is 3x1 plus 4x2. I've got two variables. I've just numbered them. x1 and x2 greater than or equal to 0. Not the same thing as being positive. They could be equal to 0. And also here I've got two constraints. 2x1 plus 5x2 less than or equal to 300. 4x1 plus 5x2 less than or equal to 450. And those are the two linear constraints, both with less than or equal to symbols. All right. Now we're going to need to introduce two slack variables for the two restrictions. So for the slack variables here, let's introduce S1 for the first inequality and S2 for the second inequality. S1 represents how much of the 300 we're not using. So S could be as much as 300, but it is greater than or equal to 0 as well. S2 represents how much of my 450 requirement I am not using. And again, that's a number that's greater than or equal to 0, but less than or equal to 450. That means I can take these two inequalities and turn them into equations and get the first tableau. So the first two steps in the simplex method are, step 1, convert inequalities to equations using slack variables, and step 2, create the tableau. So let's do that first. And here I've got the initial tableau. Of course, we put the basic variables first and the slack variables second, followed by the quantity to be maximized, followed by a column of constants. And remember that when we have a column of constants, we always separate with a vertical divider. And then we've got our two constraints at the beginning two rows with a vertical divider followed by our objective function. And I've written out the corresponding equations here on the right, turning the two inequalities into equations by letting S1 and S2 be the amount unused by x1 and x2. So now that we've got the first tableau, now we have to come up with a strategy for figuring out the optimal solution. Well, in this case, we want to maximize P. And remember that P is 3x1 plus 4x2. And if it were me, I'd really want to increase x2 by the most because it's going to provide more to the profit P. So this is our next step in the simplex method. Here along the bottom row, you can see that there are two negative values, -3 and -4. Of course, when they are moved to the opposite side of the equation, they become positive values, and the largest of those is going to contribute the most to profit. So, step 3 here is to choose the column with the largest negative entry in the last row. Now, if you ever see that there's a tie and there are two values that are both as large and negative, then choose either of these two columns. And what we do with that column is we make that our new pivot column. You can kind of see that our initial tableau has 3 columns that are entirely zeros except for a single entry of 1. That would be the two slack variables and our profit. You can see that right now, those would be the 3 columns that look like they've had some kind of pivot operation in order to make a 1 with zeros above or below. But what we do is, at this point in time, we are going to choose x2 because it seems to contribute the most to profit, and we want that to become part of our solution. Seems like to get a better solution, we should make x2 as large as possible. But how large can we make x2? Well, take a look at these equations here on the right. Using the corresponding equations, the first equation, if we wanted to make x2 as big as possible, we should let x1 be 0. We should let s1 be 0. And you can see that the number of x2 that is as great as possible would be just 300 divided by 5, which gives us 60. Now that's just a very quick ratio. We can do that right off of the side here of our tableau. 300, which is the entry in the constant column, divided by the entry in our pivot column will give us 60. Making x2 any more than 60 is going to cause either x1 or our slack variable s1 to have to be negative, and those aren't allowed. In the second equation, trying to make x2 as big as possible can be done by letting x1 equal 0 and s2 equal 0. Because remember, they are greater than or equal to 0. And that means if we want to find out how big x2 can be, we're just going to take our 450 and divide that by 5. 450 over 5 is 90. Now, by looking at those two potential values, it seems that our first constraint is more restricting than our second constraint. According to our first constraint, if we make x any bigger than 60, one of the other variables has to become negative. So we definitely can't make it be 90. And we should really just try to make x2 equal to 60. And that's what we're going to do. We're going to take all of these ratios and choose the smallest one, and that is where we're going to form the pivot row. And that's the next step of the simplex method. Now keep in mind, none of the variables can be negative, right? So if in the pivot column you have negative entries in the constraint equations, then we shouldn't consider those ratios as being important to calculate. We're only going to look at positive entries in the pivot column. Divide the entries in the constant by those entries and find the one with the smallest ratio. And again, if there's ties, just choose either one. That's fine. In this case, we are going to be choosing our first entry in the column as our pivot position. And you know what pivoting means. We're going to have to take that 5, transform it into a 1, and then we're going to have to clear out the entries above or below. Well, this is a great time for you to pause the video and try it out yourself and see what it looks like after doing the first pivot operation. Okay, you can check your answer here and see if you've done the pivot operation correctly. You can see now that x2 is a pivot column, s2 is a pivot column, and p, our profit, is a pivot column. At any point in time, we can start to see how the solution is turning out by looking at the bottom right-hand corner. Initially, we start off with a profit of 0, and we try to increase that by increasing the value of x2 to 60. And as a result, in the bottom right-hand corner now, we're looking at 240. But can we still continue to increase that profit? Well, I see I still have a negative value down here at the bottom left. That's going to help to indicate whether or not we've reached the final tableau, the final step of the simplex method. We're going to take a look and see if there's any more negative entries left. And if there is a negative entry, then we can perform the same routine starting from step 3. And it appears in this case that our work is not quite done. So we're going to take a look at trying to get x1 as our next pivot column, and we'll form the ratios again. So focusing on only the column x1, take the constants and divide by the coefficients of x1 in the two constraint rows. They're both positive, so we're going to take 60 and divide that by 2/5. And that leaves us with 150. And we're going to do the same thing in the next row. 150 divided by 2 is 75. And thinking back to step 3 and 4 here, We've picked the column, and the row is going to be the smallest positive ratio. So we're going to change our pivot from S2, move that over here to the X1 column. We would say that X1 is entering the solution and S2 is going to be exiting the solution. So there's always a pivot operation where one variable becomes our new pivot column and another variable is going to exit out and no longer be a pivot column. To try this out, we need to do a pivot operation around second row, first entry. And again, you can pause the video here, try it out for yourself, and see if you can get the solution to the next tableau. And here is what it looks like after that pivot operation. You can see that the pivot columns are X1, X2, and P. And notice as well that our choice of where we're pivoting is always going to leave P as a pivot column. There's always going to be a 1 there, and that's great because the corresponding equation here, if you want to change this to maybe a decimal, in this last row, we've got 0.1 times the first slack variable plus 0.7 times the second slack variable plus P equals 345. P is trying to be as big as possible, and right now it's 345 minus the values of 0.1 S1 and 0.7 S2. And a maximum solution here is going to be when S1 and S2 are both equal to 0, 345. And so we can kind of see how we actually get the solution. Whenever we have two non-pivot columns, we are going to treat those as 0. The columns with pivot entries are going to be the ones that give us the solution. So assigning the values of 0 to both slack variables in this case, that means we can read out the first row as x2 simply just has to equal 30. And the second row, since both slack variables are equal to 0, is simply x1 must equal 75. And of course, that's just what we need for x1 and x2 to get the optimal solution. The optimal value of p is on the bottom row, where the objective function. S1 and S2 are both equal to 0, so we just simply have p equals 345. The maximized value is just in that bottom right-hand corner. Now, it's worthwhile noting that in this example, the two slack variables end up not being in the solution. That's not always going to be the case. It really depends on what the restrictions are, especially when we start increasing the number of variables. Sometimes when we have multiple variables, more than 2, and if we have several constraints, it might not be possible to be at the maximum value of all of the constraints. We're going to have some slack. We're going to have some values or resources not being fully used to maximize profit. And then in those cases, the slack variables are going to be part of the solution. And you might have to do a little bit more work to figure out what x1 and x2 or x3 are. But this gives you a pretty good idea, at least, of how to implement the simplex method. Now, in a future video, I can show you actually how to put this information into a program. It's actually pretty straightforward to do in Excel. So since Excel is pretty accessible, I think that's a great strategy for learning how to get a computer to do all this hard work. We'll take a look at sort of larger examples, and you can still do them by hand, but they get tricky. And when we want to do minimization problems or have even more bizarre constraints in there, maybe we need like integer constraints where x1, x2 can't be decimals, things like that. Well, then you're going to have a real tough time trying to do that by hand. It's better off to see how you can implement that on a computer. But we'll save that for a future video. Thanks for watching. I'll see you again later.